these things are, when I visited you 2 years ago in Berkeley, I had already presented more or less some of these results, perhaps you remember. It turns out that there are very important and interesting links with something else, which is called the Schrödinger equation in phase space, about which I talked last year here in Askloster, so I will not talk about that again. The Schrödinger equation in phase space, okay, many physicists would be very upset by this, of course, but I mean this exists, and it's very easy to construct one by mimicking Bartman transform stuff and all this. All you have to do is actually to construct an isomorphism or isometry, sorry, from L2 Rnx, the usual Hilbert space for quantum states, an isometry of this onto a closed subspace of L2 of R2nz. And this is very easy to do. You can do it in infinitely many ways using the so-called wave packet transforms. And it does not contradict the Stone-von-Neumann theorem at all, because many people claim, yeah, but you cannot do this because of the Stone-von-Neumann theorem, you know, about the uniqueness of irreducible representations of the Heisenberg algebra. Because Stone-von-Neumann theorem says that you have a unique representation of the Heisenberg algebra in L2 Rnx. It says nothing about isomorphic copies, of course, of L2 Rnx. And it works, and this is published the results in 2 papers in Journal of Physics A, which is one of my favorite journals, because they are very quick, in 2005. And oh, okay. And by the way, I'm working now with a conjoint paper with José Isidro, a Spanish physicist, because he opened my eyes on something. It amounts to have a gauge theory, to use this Schrödinger equation in phase space. A gauge theory where the notion of gerbe, or gerb, as it's called in English, plays a crucial role. I don't know if you know, but Freddie knows certainly what a gerb is. It's a generalization of the notion of fiber bundle, where you have co-cycles. It's a little bit of Czech cosmology. That's one way of seeing things and all this. And I didn't realize that actually, but he does things like a physicist, so I have to be behind, of course, and do it correctly then. Correct everything. But I think so. It's totally related to this uncertainty principle. So that's why I called my talk "Nothing." It's much ado about nothing, but really from nothing you can do apparently lots of stuff. So perhaps it's, I don't know what.
This is great. It's half past.
It's fine. I'm good. Right, okay, so thank you very much. And if you have questions now.
Thank you.
Answer your questions?
Yes. You say you don't know how to add your
no.
squeeze states.
But the squeeze states, yes. But
yes,
the corresponding geometric.
But as you said, of course, you can use them as a basis for Hilbert space where your states lie in. Then to form some state, you would need linear combinations. So
yeah.
You would need to.
Exactly. Of course, I could transport the structure, of course, on my phase space, but I mean, is there any intuitive way of seeing things?
Yeah.
I'm not sure. So if you have ideas, they are very welcome.
Perhaps optics would give you a little way of looking at it. Namely, the G can be regarded as an optical shift.
Yes. Yes.
Of some optical device.
Yeah, yeah.
And then that squeezed state stays together. It is not broadened, and it's of course directly related to your plots.
Okay.
That's a communication in a way.
Exactly. Yeah.
And that's also the basis.
I would have a basis consisting of ellipsoids, the basis for what? Would it be for arbitrary sets in R2N? What kind of subsets? I mean, this might be much more delicate than it seems. I don't know. I'm thinking about it.
And I think it's a cover of the phase space.
Yes.
It's just a cover. It's not a partition or something.
No. It's not a partition. It's a cover. It's a cover. Absolutely. It's a cover. And you can, by the way, calculate the dimension because you can identify this phase space with the inhomogeneous symplectic group divided by the stabilizer of, I think it's ON if I remember well. So by dimension count you can get the dimension of this, but I don't remember exactly. I made some calculations. I don't know if it's useful now, but I mean, it gives a geometric picture of what is going on. And it would be also nice to try to see if one could improve the Weil theorem, you know, on a number of eigenstates which is contained in a phase space region and so on, you know, by formula and all this, by making appeal to the notion of symplectic capacity. Which the notion of symplectic capacity, by the way, has nothing to do with the notion of volume. It's something which has the dimension of an area, pi r squared. Okay. And this is a typical feature of symplectic geometry. Symplectic geometry is the geometry of area, not of volume. That's why you have so many misunderstandings about in general we have about Liouville theorems, the interpretation of Liouville's theorem, which is much more restrictive in Hamiltonian mechanics. You know?
Morris, have you ever thought, since this three-state works in optics,
Yeah.
you use the Fock space to discuss.
Yes, it's more or less equivalent.
Yeah, but what does the capacity do in Fock space? And how do you?
I don't know.
Okay, no, I just wondered if you.
I don't know. This is